On April 10th, 2019, humanity witnessed something that should have been impossible. The Event Horizon Telescope, a network of radio dishes scattered across the globe, captured the first direct image of a black hole. The target was M87 Star, a supermassive black hole lurking in the heart of a distant galaxy, 55 million light-years away. What we saw defied our everyday understanding of how the universe works. The image showed a glowing ring of light surrounding a dark void. That void, the shadow of the black hole itself, appeared as a perfect circle of absolute darkness against the brilliant backdrop of superheated matter spiraling toward its doom. But here lies the paradox that has puzzled scientists for over a century. Light, as we know it, has no mass. It weighs nothing. So how can something with no mass be trapped by gravity? This question strikes at the very heart of what we think we know about the universe. In our daily experience, gravity pulls on things that have weight. Drop a stone and it falls to the ground. Throw a ball and gravity curves its path downward. But light seems to travel in perfectly straight lines, unaffected by the gravitational pull of planets, stars, or even the sun itself. At least, that's what our intuition tells us. Yet the image from M87 Star tells a different story entirely. Here was undeniable proof that gravity doesn't just influence light, it can trap it completely. The dark circle at the center of that historic photograph represents a region where light cannot escape, no matter how hard it tries. Every photon that crosses that invisible boundary is doomed to spiral inward forever, never to return to the outside universe. To understand this seeming impossibility, we need to abandon our everyday notions of how gravity works. The truth is far stranger and more beautiful than anything our intuition could have prepared us for. Gravity, as Einstein revealed over a century ago, isn't really a force at all. It's something far more fundamental, something that touches the very fabric of reality itself. Imagine you're walking across a perfectly flat field on a clear day. You can walk in any direction you choose, in perfectly straight lines that stretch to the horizon. Now imagine that same field, but with invisible hills and valleys carved into it. You can't see these undulations, but as you walk, your path naturally curves around them. You're still walking forward with the same effort as before, but the landscape itself guides your journey in ways you never intended. This is closer to how gravity actually works. Mass and energy don't pull on objects through some mysterious force, reaching across empty space. Instead, they warp the very fabric of space and time itself, creating invisible hills and valleys in the geometry of reality. Objects, including light, simply follow the straightest possible paths through this curved landscape. When we say a black hole has an escape velocity, we're describing something profound about the shape of space-time in its vicinity. Escape velocity is the minimum speed needed to break free from a gravitational field. For Earth, that velocity is about 11 kilometers per second. Launch a rocket at that speed, and it will coast away from our planet forever, never to return. For the Sun, escape velocity is much higher, about 618 kilometers per second. But even this tremendous speed is still far less than the speed of light, which travels at nearly 300 million meters per second. This is why light from the sun reaches us every day, streaming across the solar system at its maximum possible speed. But what happens when we encounter an object so massive, so dense, that its escape velocity approaches the speed of light itself? This is where black holes enter our story. At a certain critical distance from the black hole's center, the escape velocity equals exactly the speed of light. This boundary is called the event horizon, and it represents a point of no return, more absolute than anything else in the known universe. Here's the crucial insight that resolves our paradox. Light doesn't get trapped because some force reaches out and grabs it. Light gets trapped because the black hole has curved space-time so severely that all possible paths lead inward. It's not that light lacks the strength to escape. It's that escape itself has become geometrically impossible. Think of it this way. On a normal day, if you shine a flashlight in any direction, the light travels in a straight line away from you. Near a black hole, space-time is so warped that what we call a straight line curves back on itself. The light is still traveling in the straightest possible path, but that path no longer leads to freedom. This concept challenges our most basic assumptions about space and time. We're used to thinking of space as a fixed stage where events unfold, and time as a universal clock ticking at the same rate everywhere. Einstein's revolution was to show us that space and time are not separate entities, but aspects of a single, flexible fabric that can be stretched, compressed, and twisted by the presence of mass and energy. The mathematics of this idea are elegant but complex. Einstein's field equations describe precisely how mass and energy curve space-time, and how that curvature guides the motion of everything from planets to photons. When applied to objects of extreme density, these equations predict the existence of regions where the curvature becomes so severe that not even light can climb out of the gravitational well. The Event Horizon Telescope image of M87 star provides dramatic confirmation of these theoretical predictions. The glowing ring we see isn't the black hole itself, but rather the last light we can observe before it disappears forever behind the event horizon. This light comes from matter heated to billions of degrees as it spirals inward, glowing brilliantly in its final moments before crossing the point of no return. The shadow at the center of the image corresponds almost exactly to what Einstein's equations predicted we should see. The size of the shadow, its shape, even the way the light appears brighter on one side than the other, all match the theoretical expectations with stunning precision. This wasn't just a photograph, it was a direct test of our understanding of gravity in the most extreme conditions the universe has to offer. But the mystery of how black holes trap light opens up even deeper questions about the nature of reality itself. If space and time can be warped and twisted, if the very geometry of the universe is flexible and dynamic, then what does this mean for our understanding of existence? Are there other ways that extreme gravity might surprise us? The journey to answer these questions will take us from the elegant mathematics of general relativity to the cutting edge of modern astrophysics. We'll explore the invisible architecture of space-time, venture to the very edge of black holes, and discover how these cosmic monsters both destroy and create, trapping light while simultaneously powering some of the brightest objects in the universe. Our story begins with a simple question about light and gravity, but it will lead us to profound insights about the nature of space, time, and reality itself. The black hole in M87 star isn't just a distant astronomical curiosity. It's a window into the deepest workings of the cosmos, a natural laboratory where the most extreme physics in the universe plays out on a stage visible to our telescopes. As we embark on this journey together, we'll discover that the universe is stranger, more beautiful, and more interconnected than we ever dared imagine. The mystery of how black holes trap light without touching it will reveal itself to be not just a question about gravity, but a fundamental insight into the very fabric of existence itself. To understand how black holes can trap light without touching it, we must first journey back to 1915, when a young patent clerk turned theoretical physicist named Albert Einstein published a paper that would forever change our understanding of reality. His theory of general relativity didn't just provide new equations for gravity, it revealed that gravity isn't what we thought it was at all. For over 2 centuries, scientists had relied on Isaac Newton's description of gravity as a force that somehow reached across empty space, pulling objects toward each other with invisible hands. This picture worked remarkably well for most purposes. It predicted the orbits of planets, the trajectory of cannonballs, and the motion of the tides with impressive accuracy. But it left a troubling question unanswered. How does gravity know to act instantaneously across vast distances of seemingly empty space? Einstein's revolutionary insight was to propose that space and time themselves are not the rigid, unchanging stage that Newton had imagined. Instead, they form a dynamic, flexible fabric that can be stretched, compressed, and curved by the presence of mass and energy. In this new picture, what we experience as gravity is simply the result of objects following the straightest possible paths through this curved geometry. Imagine a bowling ball placed on a stretched rubber sheet. The heavy ball creates a depression, warping the flat surface into a curved landscape. Now roll a marble across this sheet. Instead of traveling in a straight line, the marble will curve around the depression, appearing to be attracted to the bowling ball, but no force is pulling the marble toward the ball. The marble is simply following the straightest available path across the curved surface of the sheet. This analogy, while imperfect, captures the essence of Einstein's insight. Massive objects like stars and planets warp the fabric of space-time around them, creating what we might call gravitational wells. Other objects, from planets to particles of light, follow the geometry of this curved space-time, creating the illusion of a mysterious force acting at a distance. The mathematical framework that Einstein developed to describe this curvature is breathtakingly elegant. His field equations relate the curvature of space-time at any point to the mass and energy present at that location. The more massive an object, the more severely it warps the surrounding space-time. The closer you get to a massive object, the more extreme the curvature becomes. But here's where Einstein's theory makes a prediction that seems to contradict our everyday experience. If gravity is really just curved space-time, then everything should follow the same paths through this curvature, regardless of their mass. A feather and a hammer dropped in a vacuum should fall at exactly the same rate, not because they experience the same gravitational force, but because they're both following identical geodesics through curved space-time. This prediction was spectacularly confirmed by Apollo 15 astronaut David Scott on the Moon in 1971. With no atmosphere to create air resistance, he simultaneously dropped a hammer and a feather, and they hit the lunar surface at exactly the same moment. The experiment demonstrated that Einstein's geometric view of gravity was correct. Mass doesn't determine how objects respond to gravity. If mass doesn't matter for gravitational effects, then what about massless particles like photons? This is where Einstein's theory makes its most startling prediction. Light, despite having no mass whatsoever, must also follow the curved geometry of space-time. Photons travel along what physicists call null geodesics, the straightest possible paths through curved space-time for objects moving at the speed of light. This prediction seemed almost too strange to believe when Einstein first proposed it. Light bending around massive objects. It challenged the fundamental assumption that light always travels in perfectly straight lines. But Einstein was confident enough in his theory to make a specific, testable prediction. During a total solar eclipse, when the sun's glare wouldn't overwhelm the light from distant stars, astronomers should be able to observe starlight bending around the sun's edge. The opportunity came during the solar eclipse of May 29, 1919. Two expeditions, led by British astronomer Arthur Eddington, travelled to observe the eclipse from different locations. Their photographs showed that stars appeared slightly displaced from their normal positions, exactly as Einstein's theory had predicted. The amount of deflection matched the theoretical calculation with remarkable precision. This observation marked a turning point in our understanding of the universe. For the first time, we had direct evidence that space and time are not fixed and absolute, but dynamic and responsive to the presence of mass and energy. Light, the most fundamental messenger of information in the cosmos, was shown to be guided by the invisible architecture of curved space-time. The implications of this discovery extend far beyond academic physics. If light can be bent by gravity, then the universe doesn't look the way we think it does. Distant galaxies appear in slightly different positions than their true locations. The light from stars behind the sun gets deflected, creating the possibility of gravitational lensing effects that can magnify and distort the images of objects billions of light years away. But Einstein's equations predicted something even more extreme. If you could compress enough mass into a small enough volume, the resulting curvature of space-time would become so severe that certain regions would be cut off from the rest of the universe. Light trying to escape from these regions would find that all possible paths curve back inward, making escape geometrically impossible. The German physicist Karl Schwarzschild worked out the mathematical details of this extreme case just months after Einstein published his theory. Tragically, Schwarzschild died of an illness contracted while serving on the Russian front during World War I, just days after completing his calculations. But his solution to Einstein's equations revealed the theoretical possibility of objects so dense that they would trap light forever. The Schwarzschild solution describes the curvature of space-time around a perfectly spherical, non-rotating massive object. At a certain critical distance from the center, called the Schwarzschild radius, something remarkable happens. The curvature becomes so extreme that the escape velocity equals the speed of light. Inside this radius, no signal of any kind can reach the outside universe. For decades, most physicists regarded these solutions as mathematical curiosities rather than physical realities. The idea that nature could produce objects dense enough to trap light seemed too extreme to take seriously. Stars, after all, are supported against gravitational collapse by the outward pressure of nuclear fusion in their cores. How could anything become dense enough to create such extreme curvature? The answer came from studying the life cycles of massive stars. When a star much heavier than our Sun exhausts its nuclear fuel, the outward pressure that has supported it throughout its life suddenly disappears. Gravity takes over completely, compressing the star's core to densities that exceed anything found elsewhere in the universe. If the star is massive enough, nothing can stop this collapse. The core shrinks past the Schwarzschild radius, creating what we now call a black hole. The name black hole was coined by physicist John Wheeler in 1967, capturing the essence of these objects perfectly. They appear black because no light can escape from within their boundaries. They are holes in the sense that anything falling past the event horizon disappears from our observable universe forever, as if it had fallen through a hole in the fabric of reality itself. But the term hole might be misleading in one important sense. Black holes aren't empty voids in space. They are regions where space-time curvature has become so extreme that our normal concepts of space and time break down. They represent the ultimate expression of Einstein's insight that gravity is geometry. Near a black hole, the geometry of space-time becomes so warped that it fundamentally alters the nature of existence itself. The mathematics that describe this extreme curvature are complex, but the underlying concept is elegant in its simplicity. Black holes don't trap light by exerting some mysterious force. They trap light by reshaping the very paths that light can take through space-time. It's not that light lacks the energy to escape, it's that escape routes simply don't exist in the curved geometry near the black hole. This geometric understanding of gravity helps us make sense of many phenomena that would otherwise seem paradoxical. Why does light bend around massive objects? Because massive objects curve the space through which light travels. Why do clocks run slower in strong gravitational fields? Because time itself is part of the flexible fabric of space-time that gets warped by mass and energy. The realization that gravity is geometry rather than force represents one of the most profound shifts in human understanding, since Copernicus showed us that Earth is not the center of the universe. Einstein revealed that space and time, which had seemed like the most fundamental and unchangeable aspects of reality, are actually dynamic and malleable. This new understanding opened up entirely new ways of thinking about the cosmos. If space-time can be curved by mass and energy, then the universe itself must have a shape determined by its total mass and energy content. The curvature of space on the largest scales determines whether the universe is finite or infinite, whether it will expand forever or eventually collapse back on itself. Einstein's curved universe also predicts phenomena that seemed like science fiction when first proposed, but have since been confirmed by observation. Gravitational waves, ripples in the fabric of space-time itself, propagate outward from accelerating masses at the speed of light. These waves were finally detected directly by the Laser Interferometer Gravitational Wave Observatory in 2015, nearly a century after Einstein first predicted their existence. The geometric nature of gravity also explains why nothing, not even light, can travel faster than the speed of light in vacuum. The speed of light isn't just the maximum speed for electromagnetic radiation. It's the speed at which causality itself propagates through the universe. It's the speed at which changes in the curvature of space-time can spread from one location to another. As we stand on the threshold of exploring black holes in detail, Einstein's geometric picture of gravity provides the essential foundation for understanding these exotic objects. Black holes are not monsters that reach out and grab passing light rays. They are regions where the normal geometry of space-time has been so severely distorted that the very concept of escape loses its meaning. The journey from Newton's force-based picture of gravity to Einstein's geometric understanding represents more than just a change in scientific theory. It represents a fundamental shift in how we understand the nature of reality itself. Space and time are not the fixed stage on which cosmic drama unfolds. They are dynamic participants in that drama, shaped by every star, planet, and particle in the universe. This insight leads us naturally to consider what happens when curvature becomes extreme. When the gentle warping of space-time around ordinary stars and planets gives way to the violent distortions found near black holes. As we'll discover in our next exploration, there exists a critical boundary around every black hole, a point of no return, where the curvature of space-time reaches a kind of mathematical infinity. This boundary, the event horizon, represents the ultimate expression of Einstein's curved universe. The event horizon represents the most absolute boundary in the known universe. It is a spherical surface surrounding every black hole, marking the point where escape becomes impossible, not just difficult or unlikely, but geometrically forbidden by the structure of space-time itself. To understand this remarkable boundary, we must explore one of the most counterintuitive concepts in physics: how the same event can appear completely different depending on where you observe it from. Imagine you're watching a friend approach a black hole. From your safe distance, you would witness something deeply unsettling. As your friend falls toward the event horizon, time appears to slow down dramatically around them. Their movements become sluggish, their voice drops in pitch, and the light reflecting from their body shifts toward longer, redder wavelengths. At the moment they reach the event horizon, they would appear to freeze completely, their image growing dimmer and redder until it fades away entirely. To you, the outside observer, your friend never actually crosses the event horizon. They seem to hover there forever, gradually disappearing as their light gets stretched to wavelengths your eyes can no longer detect. This is one of the most profound manifestations of Einstein's relativity. Time itself runs differently in different gravitational environments, and these differences become extreme near black holes. But what about your friend's own experience? From their perspective, nothing unusual happens when they cross the event horizon. They don't feel frozen in time. They don't notice any dramatic slowing of their clocks or any sudden change in the physics around them. They simply continue falling, completely unaware that they've crossed a boundary that makes their return to the outside universe forever impossible. This dramatic difference in perspective reveals something fundamental about the nature of the event horizon. It's not a physical surface like the boundary of a planet or star. There's no material barrier, no force field, no sudden change in the local physics. The event horizon is purely a geometric consequence of extreme space-time curvature, a coordinate artifact that separates regions with fundamentally different causal relationships to the rest of the universe. The precise location of the event horizon depends only on the mass of the black hole. For a non-rotating black hole, the Schwarzschild radius formula gives us the exact distance from the center, where escape velocity equals the speed of light. This radius is remarkably small compared to ordinary astronomical objects. A black hole with the mass of our Sun would have an event horizon only about 3 kilometers from its center. Earth, if somehow compressed to form a black hole, would have an event horizon with a radius of less than 1 centimeter. These tiny distances might seem to suggest that black holes are insignificant specks in the cosmic landscape, but this impression is misleading. The event horizon represents the size of the region from which no information can ever reach us, making it the effective boundary of the black hole as far as the outside universe is concerned. Everything inside this boundary is causally disconnected from the rest of reality. The concept of causal disconnection is crucial to understanding why the event horizon represents such an absolute boundary. In physics, cause and effect are limited by the speed of light. No signal, no influence, no information of any kind can travel faster than light. This means that events happening right now in distant parts of the universe cannot influence what happens here until light has had time to travel between those locations. Near a black hole, the curvature of space-time becomes so severe that light rays trying to escape from inside the event horizon find that their paths curve back toward the black hole's center. It's not that the light lacks energy or that some force is pulling it back. The geometry of space-time itself makes outward-directed paths impossible. Every direction that looks like up and out to someone falling past the event horizon actually leads further inward when viewed from the perspective of the curved space-time geometry. This geometric impossibility of escape has profound implications for the physics of black holes. Once an object crosses the event horizon, it becomes completely isolated from the outside universe. No information about what happens to that object can ever reach external observers. From the outside perspective, the object effectively ceases to exist as an active participant in the universe's ongoing story. But this raises a puzzling question about the nature of time near black holes. If objects appear to freeze at the event horizon when viewed from outside, but experience normal time passage from their own perspective, which viewpoint represents the true passage of time? Einstein's relativity tells us that both perspectives are equally valid. There is no universal clock that ticks at the same rate everywhere in the universe. The difference between coordinate time and proper time becomes crucial for understanding black hole physics. Coordinate time is what distant observers measure with their clocks, while proper time is what someone experiences locally. Near a black hole, these two measures of time diverge dramatically. What takes a finite amount of proper time for a falling observer corresponds to an infinite amount of coordinate time for someone watching from far away. This time, dilation effect has practical consequences for black hole observations. When astronomers observe matter spiraling into black holes, they see the material's light getting redshifted and dimmed as it approaches the event horizon. The hot gas in accretion disks around black holes glows brilliantly at large distances, but this emission appears to cut off abruptly at a certain radius. This cutoff corresponds to the last stable circular orbit around the black hole, beyond which material inevitably spirals past the event horizon. The mathematics describing the event horizon reveal another surprising feature. The horizon's area can never decrease. This is known as Hawking's area theorem, and it has profound implications for black hole physics. When two black holes merge, the area of the resulting event horizon must be at least as large as the sum of the original horizon's areas. When matter falls into a black hole, the horizon area increases proportionally. This area law connects black hole physics to thermodynamics in unexpected ways. The area of the event horizon behaves remarkably like the entropy of a thermodynamic system, a measure of the information content or disorder contained within. This connection suggests that black holes might have temperatures, and that information falling past the event horizon might not be truly lost, merely scrambled in ways that make it inaccessible to outside observers. The event horizon also serves as a one-way membrane for information flow. Information can cross the horizon from outside to inside, but never in the reverse direction. This creates what physicists call the black hole information paradox. According to classical general relativity, information that falls past the event horizon is lost forever. But quantum mechanics suggests that information cannot be destroyed, only transformed or scrambled. Resolving this paradox remains one of the most challenging problems in theoretical physics. Some proposed solutions suggest that information might be encoded on the event horizon itself, stored in subtle correlations between quantum fields that an outside observer could potentially decode. Others propose that black holes might not have true event horizons at all, but rather apparent horizons that allow information to eventually escape through quantum processes. The event horizon's role as an information boundary has led to fascinating insights about the relationship between gravity and information theory. Some physicists now suspect that space-time itself might emerge from more fundamental information theoretic processes, with black hole horizons serving as natural laboratories for testing these ideas. From an observational standpoint, the event horizon presents unique challenges. By definition, we cannot directly observe anything that happens inside the horizon. However, we can study the horizon's effects on nearby matter and light. The Event Horizon Telescope. Images of black holes actually show the shadow cast by the event horizon against the bright background of the surrounding accretion disk. The size and shape of this shadow depend on the black hole's mass and spin. For a non-rotating black hole, the shadow is perfectly circular and has a diameter about 2.5 times the Schwarzschild radius. For rotating black holes, the shadow becomes slightly distorted, providing information about the black hole's angular momentum. The event horizon also affects the polarization of light passing near it. As electromagnetic radiation travels through the curved space-time around a black hole, its polarization direction rotates in predictable ways. By measuring these polarization effects, astronomers can map the magnetic field structure in the immediate vicinity of the event horizon and study how these fields interact with infalling matter. The concept of multiple event horizons adds another layer of complexity to black hole physics. For rotating black holes, described by the Kerr metric, there are actually two horizons. The outer horizon, called the event horizon, marks the boundary beyond which escape is impossible. The inner horizon, called the Cauchy horizon, marks a region where the predictive power of general relativity breaks down due to instabilities in the space-time geometry. Between these two horizons lies the ergosphere, a region where space-time itself is dragged around by the black hole's rotation. Objects in the ergosphere cannot remain stationary relative to distant observers. They are forced to rotate along with the surrounding space-time. This frame dragging effect offers the theoretical possibility of extracting energy from a rotating black hole through the Penrose process, though such extraction would be extraordinarily difficult to achieve in practice. The formation of event horizons during gravitational collapse represents one of the most dramatic events possible in the universe. As a massive star's core contracts past the Schwarzschild radius, the event horizon forms almost instantaneously from the perspective of distant observers. Once formed, This boundary cuts off all communication between the interior and exterior regions of space-time. The irreversible nature of event horizon formation connects to deep principles of physics concerning the arrow of time and the increase of entropy. Just as heat always flows from hot objects to cold ones, and never the reverse, matter and energy can cross event horizons in only one direction. This one-way flow contributes to the universe's overall increase in entropy and helps explain why we observe a consistent direction for time's passage. Understanding the event horizon as a geometric rather than physical boundary helps resolve many apparent paradoxes about black hole behavior. The horizon doesn't exert forces, emit radiation, or interact with matter in any direct way. It simply represents the boundary between regions of space-time with different causal relationships to the broader universe. As we prepare to explore the region just outside the event horizon, we encounter another remarkable feature of black hole geometry, the photon sphere. This is the innermost region where light can maintain a circular orbit around the black hole, though this orbit is fundamentally unstable. The photon sphere lies at precisely 1.5 times the Schwarzschild radius, creating a precarious zone where photons dance on the edge between escape and capture, their fate determined by the tiniest of perturbations in their trajectories. At exactly 1.5 times the Schwarzschild radius from a black hole's center lies one of the most remarkable and precarious regions in the universe, the photon sphere. Here, in this thin spherical shell, photons can theoretically maintain circular orbits around the black hole, dancing on the knife's edge between escape and eternal capture. But this cosmic ballet is fundamentally unstable, a delicate equilibrium that the slightest disturbance will shatter forever. To understand the photon sphere, we must first appreciate how extraordinary it is for light to orbit anything at all. In our everyday experience, light travels in straight lines from source to destination. Even when bent by gravity, as Einstein showed us, light follows geodesics through curved space-time, taking the most direct route available through the warped geometry. The idea that light could be bent into a complete circle challenges our basic intuitions about how the universe works. The mathematics of the photon sphere emerge directly from the Schwarzschild metric, the solution to Einstein's field equations that describes the curvature of space-time around a spherically symmetric, non-rotating black hole. At the photon sphere radius exactly 4.5 kilometers from the center of a solar mass black hole, the curvature of space-time reaches a precise balance point where centrifugal effects exactly counter the inward pull of gravity. But calling it a pull misses the deeper truth about what's happening here. The photon sphere exists not because gravity pulls on light, but because space-time curvature creates circular geodesics at this specific radius. A photon following such a geodesic experiences no forces whatsoever. From the photon's perspective, it's traveling in a perfectly straight line through space-time. The circular path emerges only when we map this geodesic onto our three-dimensional conception of space. The discovery of the photon sphere in the mathematics of general relativity came as a surprise to early researchers. Classical physics had no analog for this phenomenon. In Newton's theory of gravity, massless particles would be completely unaffected by gravitational fields. But Einstein's geometric picture reveals that all particles, regardless of mass, follow the contours of curved space-time. The photon sphere represents a critical transition zone in the gravitational field around a black hole. Outside this radius, photons emitted in any direction can potentially escape to infinity. Some will spiral inward and be captured. Others will follow hyperbolic trajectories and escape. But inside the photon sphere, escape becomes increasingly difficult. By the time we reach the event horizon at the Schwarzschild radius, escape becomes impossible. The instability of photon orbits at the photon sphere is absolute and unforgiving. Any photon in a perfect circular orbit at this radius exists in a state of unstable equilibrium, like a pencil balanced on its point. The tiniest perturbation, an infinitesimal gravitational wave passing through the region, a quantum fluctuation in the electromagnetic field, even the theoretical uncertainty principle will cause the orbit to decay. When a photon orbit becomes unstable, the outcome depends on the direction of the perturbation. A slight inward nudge sends the photon spiraling rapidly toward the event horizon and ultimate capture. An outward perturbation allows the photon to escape along a hyperbolic trajectory, carrying away energy from the black hole's vicinity. There is no middle ground, no stable intermediate orbits where a photon might settle. This knife-edge instability means that the photon sphere is essentially empty in any realistic astrophysical scenario. Real black holes exist in environments filled with gravitational disturbances from nearby stars, passing gas clouds, and the general turbulence of galactic dynamics. Any photon that happens to achieve a circular orbit at the photon sphere will be perturbed almost immediately, ending its brief dance around the black hole. Yet the photon sphere plays a crucial role in determining what we can observe about black holes. It defines the innermost boundary of the black hole's shadow as seen by distant observers. Light rays that pass just outside the photon sphere can escape and reach our telescopes, while those passing just inside spiral inward and disappear forever. This creates a sharp boundary in the images we capture of black holes. The Event Horizon Telescope observations of M87 star and Sagittarius A star provide direct observational evidence for the photon sphere's influence. The dark central region in these images corresponds almost exactly to the theoretical predictions for the size of the black hole shadow, which is determined by light ray trajectories at the photon sphere. The relationship between the photon sphere and the black hole shadow is precise and universal. For any spherically symmetric black hole, the angular size of the shadow as seen by a distant observer is exactly 2.6 times the Schwarzschild radius. This geometric relationship is independent of the black hole's mass, making it a powerful tool for testing our understanding of gravity in the strong field regime. But real black holes are not perfectly spherical. Most black holes rotate, some very rapidly, and this rotation dramatically affects the structure of the photon sphere. For rotating black holes described by the Kerr metric, the photon sphere becomes more complex, with different radii for photons orbiting in the same direction as the black hole's rotation versus those orbiting in the opposite direction. Prograde photon orbits, those moving in the same direction as the black hole's spin, can exist closer to the event horizon than retrograde orbits moving against the rotation. This asymmetry arises from the dragging of space-time itself by the rotating black hole. The rotating mass literally drags the fabric of space-time around with it, making it easier for photons to maintain orbits when moving with the flow rather than against it. The frame dragging effect near rotating black holes creates additional complexity in the photon sphere structure. In the most extreme case of a maximally rotating black hole, the prograde photon sphere can approach very close to the event horizon, while the retrograde photon sphere is pushed outward. This creates an asymmetric shadow that encodes information about the black hole's spin rate. Recent observations have begun to reveal these rotational effects in real black holes. The shadow of M87 star shows subtle asymmetries that suggest the black hole is rotating, though not at the maximum possible rate. As our observational techniques improve, measuring these asymmetries will provide increasingly precise determinations of black hole spin rates. The photon sphere also plays an important role in the process of gravitational lensing around black holes. Light from sources located behind the black hole can follow multiple paths around the curved spacetime, creating multiple images of the same object. Some of these light paths wind around the black hole multiple times before reaching the observer, creating what astronomers call higher-order images. These multiply-wound light paths pass very close to the photon sphere during their journey. The closer a light ray comes to the photon sphere, the more times it can spiral around the black hole before either escaping or being captured. In principle, there are infinitely many such images, each corresponding to light that has wound around the black hole an additional number of times. In practice, these higher-order images become exponentially dimmer with each additional winding, making them extremely difficult to detect. But their theoretical existence demonstrates the rich geometric structure created by strong gravitational fields. The photon sphere serves as the organizing center for this complex web of possible light trajectories. The study of photon trajectories near black holes has revealed unexpected connections between general relativity and other areas of physics. The paths that light takes in the curved space, time around black holes can be analyzed using techniques borrowed from classical mechanics, treating the problem as one of motion in an effective potential. This effective potential approach shows that the photon sphere corresponds to a maximum in the gravitational potential energy for light rays. Like a ball rolling over a hill, photons at the photon sphere exist at an unstable equilibrium point. This mechanical analogy helps physicists understand the complex orbital dynamics without getting lost in the mathematical details of curved space-time geometry. The photon sphere concept extends beyond black holes to other compact objects with strong gravitational fields. Neutron stars, white dwarf stars, and even some exotic theoretical objects like boson stars can have photon spheres if their gravitational fields are strong enough. However, for these objects, the photon sphere typically lies outside the object's physical surface, making the orbital dynamics less dramatic than in the black hole case. For black holes, the photon sphere provides a natural length scale that characterizes the strength of the gravitational field. Many important physical phenomena around black holes can be understood in terms of this characteristic radius. The accretion disk's inner edge typically lies close to the photon sphere radius, marking the transition from stable circular orbits to the rapid infall region. The relationship between the photon sphere and the innermost stable circular orbit for massive particles is particularly important for understanding black hole accretion. Massive particles like protons and electrons can maintain stable circular orbits down to a radius of 3 times the Schwarzschild radius, exactly twice the photon sphere radius. This innermost stable circular orbit marks the inner edge of most accretion disks. Material orbiting between the innermost stable circular orbit and the photon sphere exists in a state of unstable equilibrium, similar to that of photons at the photon sphere. Any disturbance will cause this material to spiral rapidly inward past the event horizon. This creates a sharp cutoff in the emission from accretion disks that astronomers can observe and use to measure black hole properties. The temperature and brightness profiles of accretion disks are also influenced by the proximity of the photon sphere. As material spirals inward toward the photon sphere radius, it heats up dramatically due to the increasing gravitational potential energy release. This creates the characteristic spectral signatures that allow astronomers to identify black holes and distinguish them from other compact objects. Theoretical studies of the photon sphere have also revealed connections to fundamental questions about the nature of space-time itself. Some proposed modifications to general relativity predict slightly different locations for the photon sphere, making precision measurements of black hole shadows a way to test our understanding of gravity in extreme environments. The photon sphere serves as a natural laboratory for studying the behavior of light in strong gravitational fields. Unlike the event horizon, which by definition cannot be directly observed, the photon sphere's effects can be measured through careful analysis of black hole images and gravitational lensing patterns. This makes it an invaluable tool for testing theoretical predictions against observational data. As our understanding of black hole physics continues to advance, the photon sphere will likely play an increasingly important role. Future space-based telescopes may be able to resolve the fine structure of black hole shadows with sufficient precision to detect the subtle effects of rotation, magnetic fields, and possible deviations from general relativity. The precarious nature of photon orbits at the photon sphere serves as a metaphor for the broader physics of black holes. These objects exist at the boundary between the familiar and the exotic, where the comfortable certainties of everyday physics give way to the strange realities of extreme curvature and relativistic effects. Standing at the photon sphere, we find ourselves at the edge of the observable universe around a black hole. Beyond this point, light can no longer maintain even unstable orbits. The inexorable pull of the curved space-time geometry takes over completely, drawing all matter and energy inward toward the event horizon and beyond. The photon sphere represents light's last stand against the overwhelming curvature of space-time, a final circular dance before the inevitable surrender to the black hole's gravitational embrace. The most profound insight about how black holes trap light comes from understanding that photons don't fall into black holes in the way we might imagine. They aren't grabbed by invisible hands or pulled by mysterious forces. Instead, they follow the straightest possible paths through a region of space-time so severely curved that all roads lead inward. This is the essence of geodesic motion in Einstein's universe, where the geometry of reality itself determines the fate of every particle of light. To grasp this concept, we must abandon our intuitive notion of falling as something that happens to objects with mass. In everyday experience, things fall because gravity pulls them downward against their natural tendency to remain at rest. A dropped stone accelerates toward the ground because Earth's gravitational field exerts a force on the stone's mass. But photons have no mass, so this picture cannot explain how black holes capture light. Einstein's revolution was to recognize that what we call gravity isn't a force at all, but rather the curvature of space-time itself. Objects don't fall because something pulls them. They follow geodesics through curved space-time, because that's the only way they can move. In this picture, a photon approaching a black hole is simply taking the straightest available path through the curved geometry, just as it always does. The mathematics of geodesics in curved space-time reveals why this geometric interpretation is so powerful. A geodesic is defined as the path of extremal length between 2 points in a curved space. In flat space-time, geodesics are straight lines. In curved space-time, geodesics follow the contours of the curvature, appearing curved when viewed from our familiar three-dimensional perspective. For photons, these paths are called null geodesics because light travels along world lines of zero length in the four-dimensional space-time metric. This mathematical description captures the fact that photons always travel at the speed of light and experience no proper time during their journey. From the photon's perspective, if we could imagine such a thing, the journey from any source to any destination takes zero time, regardless of the distance traveled. The concept of null geodesics helps us understand why photons respond to gravitational fields despite having no mass. In Einstein's theory, all particles follow geodesics through space-time, regardless of their mass or energy. The path a particle takes depends only on its initial position and velocity, not on its intrinsic properties. This is why a feather and a hammer fall at the same rate in a vacuum, and why photons bend around massive objects just as massive particles do. Near a black hole, the curvature of space-time becomes so extreme that the geodesics themselves take on bizarre properties. Outside the event horizon, some geodesics lead to escape, while others lead to capture. The boundary between these two families of geodesics defines the black hole's shadow, as seen by distant observers. Inside the event horizon, all geodesics lead inward toward the singularity, making escape geometrically impossible. The warped landscape analogy helps visualize this geometric picture, though we must be careful not to take it too literally. Imagine space-time as a flexible sheet that can be stretched and curved by the presence of mass and energy. A massive object like a star creates a gentle depression in this sheet, while a black hole creates an infinitely deep well with steep, inward sloping sides. A photon moving through this landscape follows the straightest possible path across the curved surface. Far from any massive objects, this path is a straight line across flat space. Near a star, the path curves gently around the depression created by the star's mass. Near a black hole, the curvature becomes so severe that paths leading into the well never lead back out. But this analogy has limitations. Real space-time is four-dimensional, not two-dimensional like the curved sheet. The curvature affects time as well as space, creating phenomena like gravitational time dilation that have no analog in the simple sheet model. The full mathematical description requires the machinery of differential geometry and tensor calculus to capture all the subtleties of curved space-time physics. The geodesic equation, which describes how particles move through curved space-time, reveals another remarkable feature of black hole physics. The equation contains no reference to the mass or charge of the particle being described. This means that all particles, from electrons to photons to entire spacecraft, follow identical paths through the same gravitational field if they start with the same initial conditions. This universality of geodesic motion has profound implications for understanding black holes. It means that the capture of light by black holes follows exactly the same geometric principles that govern the motion of any other object. The only difference is that photons always travel at the speed of light, which constrains their possible geodesics to the special class of null curves. The concept of tidal forces provides another perspective on geodesic motion near black holes. Tidal forces arise because different parts of an extended object follow slightly different geodesics through curved space-time. Near a black hole, these tidal effects become extreme, stretching objects radially and compressing them laterally in a process that physicists colorfully call spaghettification. For photons, which have no spatial extent, tidal forces don't directly apply, but light waves do have finite wavelengths, and the curvature of space-time can affect different parts of a light wave differently. This leads to phenomena like gravitational redshift, where light climbing out of a gravitational well loses energy and shifts toward longer wavelengths. The redshift effect provides direct observational evidence for the curvature of space-time around massive objects. Light emitted from the surface of a massive star appears redshifted when observed from a distance. Light from material spiraling into a black hole shows extreme redshift as it approaches the event horizon, eventually shifting to infrared and radio wavelengths that our eyes cannot detect. This redshift phenomenon also explains why objects appear to freeze at the event horizon when viewed from a distance. The light carrying information about the falling object becomes increasingly redshifted and dimmed as the object approaches the horizon. Eventually, the redshift becomes so extreme that the light effectively disappears from view, creating the illusion that time has stopped for the falling object. The geodesic description of photon motion also helps explain the formation of black hole shadows and Einstein rings. When light from a distant source passes near a black hole, different rays follow different geodesics through the curved spacetime. Some rays are deflected but escape, reaching the observer from apparent directions that differ from the true source location. Other rays are captured and never reach the observer at all. The boundary between captured and escaped rays creates the sharp edge of the black hole shadow. This boundary corresponds to the set of null geodesics that asymptotically approach the photon sphere before either escaping to infinity or spiraling into the event horizon. The precise shape and size of this shadow encode information about the black hole's mass, spin, and possibly other properties. Einstein ring formation occurs when a black hole lies almost exactly between a distant source and the observer. In this configuration, light from the source can reach the observer along multiple geodesics that curve around opposite sides of the black hole. The result is a ring-shaped image of the source, stretched and magnified by the gravitational lensing effect. The study of null geodesics around black holes has revealed an infinite hierarchy of possible light paths between any source and observer. Light can wind around the black hole any number of times before either escaping or being captured. Each additional winding corresponds to a weaker, more highly magnified image of the source. These higher-order images are exponentially dimmer and require extremely sensitive instruments to detect. The geodesic approach also provides insights into the information content of black hole observations. Every photon that escapes from the vicinity of a black hole carries information about the space-time geometry it has traversed. By analyzing the arrival times, directions, and frequencies of these photons, astronomers can reconstruct the gravitational field and infer properties of the black hole itself. Modern numerical simulations of geodesic motion around black holes have become increasingly sophisticated, allowing researchers to predict the detailed appearance of black holes under various observational conditions. These simulations played a crucial role in interpreting the Event Horizon Telescope images and will be essential for analyzing future observations with even higher resolution and sensitivity. The geodesic picture also illuminates the relationship between classical and quantum physics near black holes. While individual photons follow classical geodesics through curved spacetime, quantum effects can modify the statistical distribution of photon paths. These quantum corrections become important near the Planck scale, where our classical description of spacetime geometry may break down entirely. Hawking radiation, the quantum process by which black holes slowly evaporate, can be understood as arising from quantum fluctuations in the geodesic structure near the event horizon. Virtual particle pairs created by quantum vacuum fluctuations can be separated by the extreme curvature, with one member falling into the black hole while the other escapes as real radiation. The concept of geodesic motion extends beyond photons to include gravitational waves, ripples in space-time itself that propagate at the speed of light. Gravitational waves also follow null geodesics through curved space-time, making them subject to the same capture and lensing effects as electromagnetic radiation. The detection of gravitational waves from black hole mergers has opened a new window into studying these extreme objects. The geodesic description reveals why black hole capture is so efficient for photons. Unlike massive particles, which can potentially gain energy and escape from gravitational fields through various mechanisms, photons are constrained to travel at exactly the speed of light. This constraint severely limits their possible trajectories and makes escape more difficult once they venture too close to the black hole. The efficiency of photon capture also depends on the impact parameter, the closest distance a photon would approach the black hole if spacetime were flat. For large impact parameters, the geodesic curves gently around the black hole and continues to infinity. For small impact parameters, the geodesic curves so sharply that the photon spirals inward past the event horizon. The critical impact parameter that separates capture from escape defines the angular size of the black hole shadow. This critical value depends only on the black hole's mass and spin, making shadow observations a direct probe of these fundamental properties. Future observations may be sensitive enough to detect variations in the shadow size caused by the black hole's gravitational field fluctuations. Understanding photon geodesics also helps explain why black holes appear to have temperatures and emit radiation, despite being perfect absorbers of classical physics. The quantum field theory of curved spacetime shows that the event horizon acts like a one-way membrane that allows quantum information to leak out while preventing classical information from escaping. The geodesic perspective transforms our understanding of black hole physics from a story about mysterious forces capturing light to a geometric tale about the paths available through curved space-time. In this picture, black holes don't reach out and grab passing photons. Instead, they reshape the underlying geometry of reality so completely that all paths lead inward. The photons simply follow the only routes available to them through this warped landscape, unknowingly sealing their own fate by obeying the fundamental laws of motion in curved space-time. For over a century after Einstein first predicted their existence, black holes remained purely theoretical objects, mathematical solutions to equations that seemed too exotic to exist in the real universe. The idea of photographing a black hole seemed impossible by definition. How do you take a picture of something that allows no light to escape? The answer came through one of the most ambitious scientific projects ever attempted, creating a telescope the size of Earth itself. The Event Horizon Telescope represents a triumph of international cooperation and technological innovation. By linking radio telescopes across the globe, from Hawaii to Chile to Antarctica, astronomers created a virtual telescope with an effective diameter equal to the size of our planet. This technique, called Very Long Baseline Interferometry, allowed them to achieve the extraordinary resolution needed to see the shadow of a black hole 55 million light-years away. The target for this historic observation was M87 Star, a supermassive black hole at the center of the galaxy Messier 87. With a mass 6.5 billion times that of our Sun, this black hole is large enough that its event horizon, though impossibly distant, sub-tens an angle, just barely detectable by the most sensitive instruments on Earth. The angular size is equivalent to seeing a donut on the surface of the Moon. When the first image was released on April 10th, 2019, it revealed exactly what Einstein's equations had predicted. A bright ring of glowing gas surrounded a dark central region, the shadow cast by the black hole's event horizon. The shadow appeared almost perfectly circular, with a diameter of about 42 microarc seconds, matching theoretical predictions to within 10% accuracy. But this image represents far more than just a photograph. It's a map of space-time curvature itself, a direct visualization of how extreme gravity bends the paths of light. Every photon that contributed to this image followed a complex geodesic through the warped space-time around the black hole, carrying information about the gravitational field it traversed during its journey. The bright ring visible in the image comes from hot gas spiraling into the black hole at nearly the speed of light. This material, heated to billions of degrees by gravitational compression and magnetic field interactions, glows brilliantly across the electromagnetic spectrum. The asymmetry in the ring's brightness reveals the black hole's rotation, with the approaching side Doppler boosted to higher intensity, while the receding side appears dimmed. The shadow itself contains crucial information about the black hole's properties. Its size directly measures the black hole's mass, while subtle distortions in its shape reveal the black hole's spin rate and orientation. The sharp boundary of the shadow confirms that the object has an event horizon, ruling out alternative theories that propose different types of compact objects without true black holes. Gravitational lensing plays a crucial role in shaping the image we observe. Light from the glowing accretion disk doesn't just travel in straight lines to our telescopes. Instead, it follows curved paths through the warped space-time, with some rays bending around the black hole to reach us from unexpected directions. This creates multiple images of the same material, superimposed in complex ways that enhance the brightness of the observed ring. The most dramatic lensing effect creates what astronomers call the photon ring, a theoretical feature that should appear as a narrow bright band at the inner edge of the black hole shadow. This ring consists of light that has orbited the black hole one or more times before escaping. Each additional orbit creates a fainter subring, building up an infinite series of nested features that encode detailed information about the black hole's gravitational field. Current observations are not yet sensitive enough to resolve these higher-order photon rings, but future improvements to the Event Horizon Telescope may detect them. These features would provide unprecedented tests of general relativity in the strong field regime, potentially revealing deviations from Einstein's theory or confirming its predictions with extraordinary precision. The process of creating black hole images from radio telescope data involves sophisticated computational techniques that reconstruct the source brightness distribution from sparse measurements. The telescopes don't directly capture images, but rather measure correlations between signals received at different locations. Converting these measurements into pictures requires complex algorithms that must account for atmospheric effects, instrumental calibration, and the rotation of Earth during the observation. Multiple independent imaging algorithms were used to ensure the reliability of the results. Each algorithm makes different assumptions about the structure of the source, yet all produced remarkably similar images of M87 star. This consistency provides confidence that the observed features are real rather than artifacts of the imaging process. The polarization of light provides another layer of information about black hole environments. The hot gas around black holes contains magnetic fields that can align the oscillations of electromagnetic waves in preferred directions. By measuring the polarization of the radio emission, astronomers can map the magnetic field structure in the immediate vicinity of the event horizon. These polarization measurements reveal that the magnetic field near M87 star is highly organized, likely playing a crucial role in launching the powerful jet of material that extends thousands of light years from the black hole. The field structure suggests that magnetic forces help extract energy from the black hole's rotation, powering some of the most energetic phenomena in the universe. The success with M87 star led to observations of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. Despite being much closer to us than M87 star, Sagittarius, A star proved more challenging to image because of its rapid variability. The hot gas around it changes on timescales of minutes, requiring new techniques to capture a stable image. The Sagittarius A star image, released in 2022, showed a similar ring structure to M87 star, but with important differences. The shadow appeared rounder and the emission more symmetric, suggesting different viewing angles or accretion properties. These differences provide valuable insights into how black hole environments can vary while still following the same fundamental physics. The comparison between these two black holes, separated by factors of thousands in mass and millions in distance, demonstrates the universality of black hole physics. Despite their vastly different scales and environments, both objects produce shadows that match the predictions of general relativity. This consistency across such different systems provides strong evidence for the geometric nature of gravity. Gravitational lensing effects extend far beyond the immediate vicinity of black holes. Light from distant galaxies can be bent and magnified by intervening black holes, creating distorted images that reveal the presence of otherwise invisible dark matter. These weak lensing effects have become a powerful tool for mapping the distribution of matter throughout the universe. Strong gravitational lensing can create multiple images of the same distant object, sometimes arranged in beautiful symmetric patterns called Einstein rings. When a massive galaxy containing a central black hole lies almost exactly between us and a more distant source, the result can be a nearly perfect ring of light surrounding the lensing galaxy. These configurations are rare, but provide exquisite laboratories for testing general relativity. The time delay between multiple images in strong lensing systems offers another window into black hole physics. Light taking different paths around the lensing object arrives at different times, with the delay depending on both the geometry of the light paths and the gravitational redshift experienced along each route. Measuring these delays provides an independent way to determine the mass and structure of the lensing black hole. Future observations promise even more detailed views of black hole environments. Planned extensions to the Event Horizon Telescope will add more telescopes and extend observations to shorter wavelengths, improving both resolution and sensitivity. Space-based telescopes could eventually create baselines larger than Earth, achieving the resolution needed to image smaller black holes or probe closer to the event horizons of known objects. The next generation of extremely large ground-based telescopes will be able to track individual stars orbiting close to black holes, measuring the gravitational redshift and time dilation effects predicted by general relativity. These observations will test Einstein's theory in regimes even more extreme than current black hole imaging can achieve. Advanced gravitational wave detectors will provide complementary information about black holes through the ripples they create in space-time itself. When black holes merge, they produce gravitational waves that carry detailed information about the masses, spins, and orbital dynamics of the colliding objects. This gravitational wave astronomy opens an entirely new window into the black hole population throughout the universe. The study of black hole images has also revealed unexpected connections between gravity and information theory. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary. For black holes, this means that the information about everything that has ever fallen past the event horizon might be encoded in subtle correlations on the horizon's surface. This holographic encoding could potentially be detected through extremely precise measurements of the black hole shadow and its fluctuations over time. While current observations are nowhere near this sensitivity level, future techniques might be able to probe these quantum mechanical effects and test fundamental theories about the nature of information and gravity. The images of M87 star and Sagittarius A star represent more than scientific achievements. They are iconic symbols of human curiosity and ingenuity. These pictures show us objects so extreme that they challenge our understanding of physics itself. Yet they were captured using techniques that demonstrate the power of international scientific collaboration. The light captured in these images began its journey in one of the most violent environments in the universe, where matter heated to billions of degree spirals toward its ultimate fate. That light traveled for millions of years through the cosmos, carrying information about the fundamental nature of space and time, before finally reaching our radio telescopes and revealing secrets that had been hidden since the universe began. Each photon in these historic images followed a unique geodesic through the curved space-time around the black hole, experiencing gravitational effects that stretched and bent its path in precisely the ways that Einstein's equations predicted. The fact that we can now trace these light paths backward from our observations to their sources provides unprecedented confirmation of our understanding of gravity's geometric nature. As we continue to develop more sensitive instruments and sophisticated analysis techniques, black hole images will become increasingly detailed windows into the physics of extreme gravity. These observations bridge the gap between theoretical predictions and observational reality, allowing us to test the limits of our understanding in natural laboratories, where the fundamental forces of nature operate at their most extreme levels. Beyond the event horizon lies a realm that defies our ability to observe directly. Yet general relativity makes startling predictions about what happens in this hidden region. According to Einstein's equations, the interior of a black hole is not an empty void, but a dynamic region of space-time where the very concepts of space and time become twisted beyond recognition. Here, all paths lead inexorably toward the center, where our current understanding of physics breaks down completely. The journey of a photon past the event horizon reveals the strange nature of the black hole interior. From the perspective of someone falling with the photon, nothing unusual happens at the moment of crossing the horizon. There is no physical barrier, no sudden change in the local physics, no sensation of crossing a boundary. The photon simply continues following its geodesic through curved space-time, unaware that it has passed the point of no return. But the geometry of space-time inside the horizon is profoundly different from anything in our everyday experience. The radial direction, which points toward the black hole's center, becomes time-like rather than space-like. This means that moving toward the center is not a choice that can be avoided, but an inevitable consequence of the passage of time itself. Just as we cannot choose to move backward in time in normal space, nothing inside a black hole can choose to move away from the center. This geometric inevitability explains why escape from inside the event horizon is impossible. It's not that some force prevents objects from moving outward, but that the very concept of outward direction loses its meaning in the warped space-time geometry. Every direction that looks like it might lead away from the center actually leads further inward when traced through the curved space-time manifold. The mathematical description of the black hole interior requires careful treatment of coordinate systems. The Schwarzschild coordinates that work well outside the event horizon become singular at the horizon itself, creating the false impression that time stops there. More sophisticated coordinate systems, such as Kruskal-Szekeres coordinates or Eddington-Finkelstein coordinates, extend smoothly through the event horizon and reveal the true structure of the interior. In these coordinates, the black hole interior appears as a finite region of space-time with a definite beginning and end. The beginning is the event horizon, where objects enter from the outside universe. The end is the central singularity, where the curvature of space-time becomes infinite, and our current theories break down. The time between crossing the horizon and reaching the singularity is finite and depends only on the black hole's mass. For a black hole with the mass of our Sun, this journey time is measured in microseconds. For supermassive black holes like those at galactic centers, the time can extend to hours or even days. During this brief interval, any infalling matter experiences increasingly extreme tidal forces that stretch objects radially and compress them laterally in the process physicists call spaghettification. The tidal effects arise because different parts of an extended object follow slightly different geodesics through the curved space-time. Near the singularity, these differences become enormous, tearing apart any structure held together by electromagnetic or nuclear forces. Even individual atoms would be distorted beyond recognition as the gradient in the gravitational field approaches infinity. But the most puzzling aspect of the black hole interior is the nature of the singularity itself. At this point, the curvature of space-time becomes infinite, the density of matter becomes infinite, and the normal laws of physics cease to apply. The singularity represents a boundary of our current scientific understanding, a place where general relativity predicts its own breakdown. The singularity is not a point in space, but rather a moment in time, occurring at the end of every possible timeline that begins inside the event horizon. This temporal nature of the singularity reflects the strange geometry of the black hole interior, where the roles of space and time become interchanged compared to the outside universe. The existence of singularities in general relativity is deeply troubling to physicists because it represents a fundamental failure of the theory to provide meaningful predictions. At a singularity, physical quantities become infinite, which is generally interpreted as a sign that the theory is being pushed beyond its domain of validity. Most physicists believe that quantum effects will somehow resolve the singularity problem, but a complete theory of quantum gravity remains elusive. Various proposals have been made for what might replace the classical singularity. Some theories suggest that quantum effects create a bounce that connects the black hole interior to another region of space-time, possibly even another universe. Others propose that the singularity is replaced by a region of extremely high but finite curvature, where new physics beyond general relativity becomes important. String theory, one of the leading candidates for a quantum theory of gravity, suggests that the concept of point particles breaks down at very small scales. In this framework, the singularity might be replaced by extended objects like strings or higher dimensional branes, which could avoid the infinite densities predicted by classical general relativity. Loop quantum gravity, another approach to quantum gravity, proposes that space-time itself is quantized at the smallest scales. In this theory, the infinite compression toward a singularity is prevented by quantum geometric effects that create a discrete structure of space-time. The classical singularity is replaced by a quantum bridge that might connect to other regions of the universe. The information paradox adds another layer of mystery to black hole interiors. According to quantum mechanics, information cannot be destroyed, only transformed or redistributed. But general relativity suggests that any information carried by matter falling into a black hole is lost forever when it reaches the singularity. This apparent contradiction between two fundamental theories represents one of the deepest puzzles in modern physics. Some proposed solutions to the information paradox suggest that information might be preserved in subtle quantum correlations between the interior and exterior of the black hole. Others propose that the information is somehow encoded on the event horizon itself, stored in microscopic degrees of freedom that are invisible to classical physics, but become important in a complete quantum theory of gravity. The holographic principle, inspired by black hole thermodynamics, suggests that all the information about the three-dimensional interior of a black hole can be encoded on its two-dimensional boundary. This idea has led to profound insights about the relationship between gravity and quantum field theory, with applications extending far beyond black hole physics. Recent developments in holographic duality have suggested that the interior of a black hole might be intimately connected to quantum entanglement between different parts of the boundary theory. In this picture, the geometry of space-time itself emerges from quantum information processing, with the black hole interior representing a particular pattern of quantum correlations. The ADS-CFT correspondence, a specific realization of holographic duality, has provided new tools for studying black hole interiors theoretically. This correspondence relates gravity in a higher dimensional anti-de Sitter space to a conformal field theory living on its boundary. While this setup doesn't directly describe realistic black holes, it has revealed deep connections between geometry, thermodynamics, and quantum information. One of the most surprising predictions of holographic duality is that the black hole interior might be reconstructed from quantum information stored on the boundary. This suggests that the interior is not fundamental, but rather emerges from more basic quantum mechanical processes. The implications of this idea for our understanding of space and time are still being explored. The concept of black hole complementarity offers another perspective on the interior puzzle. According to this principle, the description of matter falling into a black hole depends on the observer's reference frame. An outside observer sees the matter get stuck at the event horizon and eventually evaporate away with Hawking radiation. But an infalling observer sees the matter continue smoothly past the horizon toward the singularity. Both descriptions are claimed to be equally valid, with no possibility of contradiction, because no single observer can verify both simultaneously. This principle resolves some paradoxes about information preservation, but raises new questions about the fundamental nature of reality and the role of observation in quantum mechanics. The study of black hole interiors has also revealed connections to the thermodynamic properties of these objects. Black holes behave remarkably like thermal systems, with temperatures and entropies that scale with their surface areas rather than their volumes. This connection suggests that the microscopic degrees of freedom responsible for black hole entropy might be located on or near the event horizon, rather than distributed throughout the interior. Hawking's calculation of black hole temperature and entropy relies on quantum field theory in curved space-time, treating the background geometry as classical while quantizing matter fields. This semi-classical approach predicts that black holes slowly evaporate by emitting thermal radiation, with smaller black holes evaporating faster than larger ones. The evaporation process raises profound questions about the fate of information that has fallen into the black hole. If the Hawking radiation is truly thermal, it carries no information about the interior, suggesting that information is destroyed when black holes evaporate completely. But this conclusion conflicts with the fundamental principles of quantum mechanics. Recent research has suggested that the Hawking radiation might not be exactly thermal, but could contain subtle correlations that encode information about the black hole's interior. Detecting these correlations would require extraordinary precision, but they might provide a way to resolve the information paradox without invoking exotic physics. The firewall paradox represents another challenge to our understanding of black hole interiors. Some interpretations of quantum mechanics suggest that the event horizon should be surrounded by a wall of high-energy radiation that would incinerate any infalling observer. This conflicts with the equivalence principle, which requires that local physics should appear normal to a freely falling observer. Various solutions to the firewall paradox have been proposed, ranging from modifications to quantum mechanics to new interpretations of the holographic principle. The debate continues to drive research at the intersection of general relativity, quantum field theory, and quantum information theory. The interior of rotating black holes described by the Kerr metric adds additional complexity to these theoretical challenges. Rotating black holes have an inner horizon, in addition to the outer event horizon, creating a region called the Cauchy horizon, where the predictive power of general relativity breaks down. The interior structure becomes even more exotic, with closed time-like curves and regions where causality itself becomes problematic. Some solutions to the Einstein equations describe black holes connected to other regions of spacetime through bridges called Einstein-Rosen bridges or wormholes. While these solutions are mathematically consistent, they typically require exotic matter with negative energy densities to remain stable. Whether such matter can exist in nature remains an open question. The study of black hole interiors pushes the boundaries of theoretical physics, revealing the limitations of our current understanding while pointing toward new physics that might emerge at the intersection of gravity and quantum mechanics. These investigations have implications that extend far beyond black holes themselves, touching on fundamental questions about the nature of space, time, information, and reality. While we may never be able to observe the interior of a black hole directly, the theoretical study of these regions continues to drive advances in our understanding of the universe. The paradoxes and puzzles associated with black hole interiors serve as guides toward a more complete theory of quantum gravity, one that might finally resolve the singularity problem and unify our understanding of the largest and smallest scales in nature. The journey into the theoretical heart of a black hole reveals not just the extreme physics of these objects, but also the current limits of human knowledge. At the singularity, our equations break down, our concepts fail, and we encounter the edge of the known universe. Yet it is precisely at these boundaries that the most profound discoveries often await, promising new insights into the fundamental nature of existence itself. The relationship between black holes and light reveals one of the most fascinating paradoxes in astrophysics. While black holes are defined by their ability to trap light permanently, they are also responsible for powering some of the brightest objects in the observable universe. This apparent contradiction resolves when we understand that black holes don't just consume light, they orchestrate complex processes that can create spectacular displays of electromagnetic radiation far more luminous than entire galaxies. The key to understanding this paradox lies in the distinction between light that originates inside the event horizon and light that forms in the intense gravitational and magnetic fields surrounding the black hole. Material spiraling into a black hole releases enormous amounts of energy through gravitational compression, friction, and magnetic field interactions. This energy manifests as radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. Accretion disks represent the primary mechanism by which black holes transform gravitational potential energy into radiant light. As matter spirals inward toward the event horizon, it forms a flattened disk structure supported by angular momentum. The material in this disk orbits at speeds approaching the speed of light, generating temperatures of millions or even billions of degrees through viscous heating and magnetic reconnection. The inner edge of a typical accretion disk extends down to the innermost stable circular orbit, located at 3 times the Schwarzschild radius from the black hole's center. This boundary represents the last point where matter can maintain a stable circular orbit before inevitably plunging past the event horizon. The proximity to such extreme gravitational fields creates physical conditions unlike anywhere else in the universe. Within the accretion disk, differential rotation creates shear forces that heat the material through viscous dissipation. Different parts of the disk orbit at different speeds, with inner regions moving faster than outer regions according to Kepler's laws. This velocity gradient generates friction that converts orbital kinetic energy into thermal energy, causing the disk material to glow brilliantly. The temperature profile of an accretion disk follows a predictable pattern, with the inner regions reaching the highest temperatures and emitting primarily in X-rays and ultraviolet light. Moving outward, the temperature decreases and the emission shifts to optical, infrared, and eventually radio wavelengths. This spectrum allows astronomers to diagnose the physical conditions throughout the disk and estimate the black hole's mass and spin rate. Magnetic fields threading the accretion disk play a crucial role in transporting angular momentum and enabling the infall process. Without some mechanism to remove angular momentum, material would simply orbit the black hole indefinitely rather than spiraling inward. Magnetorotational instabilities in the disk generate turbulence that efficiently transports angular momentum outward while allowing mass to flow inward. These same magnetic fields can channel material into powerful jets that extend thousands or even millions of light years from the black hole. The jets appear to be launched from the innermost regions of the accretion disk, possibly from the ergosphere of rapidly rotating black holes. The exact mechanism remains a subject of active research, but magnetic field lines that connect to the black hole's horizon may extract rotational energy through the Blandford-Znajek process. Relativistic jets from supermassive black holes rank among the most energetic phenomena in the universe. These collimated streams of plasma travel at speeds exceeding 99% of the speed of light, carrying more energy than the total output of billions of stars. When these jets interact with the surrounding intergalactic medium, they create spectacular radio sources that can be detected across cosmic distances. The relativistic motion of material in jets and accretion disks creates dramatic Doppler effects that modify the observed properties of the emitted light. Material moving toward us appears brighter and bluer due to relativistic beaming, while material moving away appears dimmer and redder. These asymmetries in brightness and color provide direct evidence for the extreme velocities involved in black hole accretion. Relativistic beaming also affects the apparent speed of features moving along jets. When a jet is pointed nearly toward Earth, geometric projection effects can make features appear to move faster than the speed of light, a phenomenon called superluminal motion. This effect was first discovered in observations of quasars and provided early evidence for the relativistic nature of black hole jets. The spectrum of radiation from black hole accretion systems contains detailed information about the physical processes occurring near the event horizon. Ion emission lines, produced when X-rays from the inner disk illuminate the disk's surface, show characteristic shapes that reveal the effects of gravitational redshift, Doppler shifts, and gravitational lensing. These line profiles provide some of the most direct probes of strong field gravity effects around black holes. Gravitational redshift causes light emitted from deep within the gravitational well to lose energy as it climbs out of the potential. This effect is most pronounced for emission from the innermost regions of the accretion disk, where it can shift X-ray photons to significantly lower energies. The magnitude of this redshift depends on the black hole's mass and the emission radius, providing a tool for measuring these fundamental properties. Time dilation effects near black holes also influence the observed properties of variable emission. Fluctuations in the X-ray output from the inner accretion disk appear stretched in time when observed from a distance, with the stretching factor depending on the gravitational redshift at the emission site. These timing effects provide additional constraints on the geometry of the emission region. The phenomenon of gravitational lensing by black holes can dramatically amplify the brightness of background sources. When a stellar mass black hole passes between Earth and a more distant star, the black hole's gravity acts like a lens that focuses the star's light and creates a temporary brightening event. These microlensing events provide a way to detect black holes that are not actively accreting material and would otherwise be invisible. Gravitational microlensing has revealed a population of isolated black holes wandering through our galaxy. These objects, formed from the collapse of massive stars, typically have masses between 5 and 50 times that of the Sun. Most remain dark and undetectable, except when they occasionally eclipse background stars through lensing effects. The study of X-ray binaries has provided crucial insights into how black holes interact with normal stars. In these systems, a black hole strips material from a companion star, creating an accretion disk that glows brilliantly in X-rays. The orbital dynamics of these systems allow precise measurements of the black hole masses, confirming that they exceed the theoretical maximum mass for neutron stars. Some X-ray binaries exhibit dramatic outbursts where the brightness can increase by factors of millions over periods of days or weeks. These outbursts are thought to result from thermal instabilities in the accretion disk that cause sudden increases in the rate of mass transfer onto the black hole. During outbursts, the inner disk can reach temperatures exceeding 100 million degrees, making it one of the hottest places in the universe. The transition between different accretion states provides insights into the physics of matter under extreme conditions. At low accretion rates, the disk structure becomes geometrically thick and radiatively inefficient, with most of the gravitational energy going into heating ions rather than producing radiation. At high accretion rates, the disk becomes thin and radiatively efficient, converting a significant fraction of the infalling mass energy into electromagnetic radiation. Hawking radiation represents a fundamentally different mechanism by which black holes can emit light. This quantum mechanical process occurs when virtual particle pairs created by vacuum fluctuations are separated by the extreme gravitational field near the event horizon. One member of the pair falls into the black hole, while the other escapes as real radiation, causing the black hole to slowly evaporate. The temperature of Hawking radiation is inversely proportional to the black hole's mass, making it extremely cold for astrophysically relevant black holes. A solar mass black hole would have a Hawking temperature of only 60 billionths of a degree, above absolute zero, far too cold to detect with any conceivable technology. Only primordial black holes, with masses much smaller than the Sun, would have detectable Hawking radiation. The power output from Hawking radiation is also inversely related to the black hole's mass, but with an even stronger dependence. This means that smaller black holes evaporate faster than larger ones, with the smallest black holes exploding in bursts of gamma rays when they finally evaporate completely. No such explosions have been detected, providing constraints on the population of primordial black holes in the universe. The information content of Hawking radiation remains one of the deepest puzzles in theoretical physics. If the radiation is truly thermal, it carries no information about the material that formed the black hole or fell into it subsequently. This apparent loss of information conflicts with the fundamental principles of quantum mechanics and has spawned decades of theoretical research into the black hole information paradox. Recent developments suggest that Hawking radiation might contain subtle correlations that encode information about the black hole's interior. These correlations would be extraordinarily difficult to detect, requiring measurements of quantum entanglement between individual photons emitted at different times. While beyond current technology, such measurements might someday provide a window into the quantum nature of black hole physics. The interaction between black holes and electromagnetic fields can also lead to particle acceleration and high-energy radiation. Magnetic field lines that thread the ergosphere of a rotating black hole can be twisted by the frame-dragging effect, building up energy that is eventually released through magnetic reconnection events. These processes can accelerate particles to ultra-relativistic speeds and produce gamma-ray emission. The study of gravitational waves has opened a new window into black hole physics that complements electromagnetic observations. When two black holes merge, they produce ripples in space-time itself that carry away enormous amounts of energy. The detection of these gravitational waves by LIGO and Virgo has revealed a previously unknown population of stellar mass black holes with properties that differ from those inferred from X-ray observations. Electromagnetic counterparts to gravitational wave events could provide even more detailed information about black hole mergers. While black hole mergers are not expected to produce significant electromagnetic emission, mergers involving neutron stars can create brilliant kilonovae that outshine entire galaxies for weeks. The combination of gravitational wave and electromagnetic observations offers unprecedented insights into the physics of these extreme events. The future of black hole electromagnetic astronomy promises even more detailed observations of the light exchange processes around these objects. Next-generation X-ray telescopes will be able to measure the detailed shapes of ion emission lines with unprecedented precision, providing new tests of general relativity in the strong field regime. Advanced radio interferometry will achieve higher resolution images of black hole shadows and jet launching regions. Space-based gravitational wave detectors will be sensitive to mergers of supermassive black holes, events that may be accompanied by spectacular electromagnetic displays as the merging black holes disrupt their surrounding accretion disks. These observations will probe the growth and evolution of the most massive black holes in the universe and their role in galaxy formation. The study of black hole light exchange has revealed these objects to be far more than simple cosmic vacuum cleaners. They are complex, dynamic systems that process matter and energy in ways that illuminate fundamental physics while creating some of the most spectacular displays in the universe. Through their gravitational and magnetic fields, black holes transform the potential energy of infalling matter into radiation that can outshine billions of stars, making them visible across cosmic distances and allowing us to study the most extreme physics nature has to offer. Black holes serve as natural laboratories where the most extreme physics in the universe plays out on scales we can observe from Earth. These cosmic laboratories allow us to test our theories of gravity, space-time, and matter under conditions that could never be replicated in terrestrial experiments. The gravitational fields around black holes are so intense that they stretch our understanding of physics to its absolute limits. revealing phenomena that exist nowhere else in the known universe. The strong field regime around black holes provides the ultimate testing ground for Einstein's theory of general relativity. While the theory has passed every test in the weak field conditions of our solar system, black holes represent environments where gravitational effects are amplified by factors of billions compared to anything we experience on Earth. Here, space-time curvature becomes so severe that it fundamentally alters the nature of matter, energy, and information itself. One of the most precise tests of general relativity comes from observing the orbits of stars around the supermassive black hole at the center of our galaxy, Sagittarius A star. These observations, conducted over decades using increasingly sophisticated telescopes, have tracked individual stars as they follow elliptical orbits with periods ranging from 16 years to several centuries. The star designated S2 provides the most dramatic example, approaching within 20 billion kilometers of the black hole during its closest approach. The orbital motion of S2 exhibits several relativistic effects that allow direct tests of Einstein's predictions. The perihelion advance, the gradual rotation of the orbit's elliptical shape, occurs at a rate that matches general relativity's predictions with extraordinary precision. This effect is similar to the famous advance of Mercury's orbit around the Sun, but amplified by a factor of thousands due to the much stronger gravitational field. During S2's closest approach to Sagittarius A star, astronomers detected gravitational redshift in the star's light that reached 2,400 kilometers per second equivalent velocity. This represents the most extreme gravitational redshift ever measured from a star, confirming Einstein's prediction that time runs slower in stronger gravitational fields. The magnitude of this effect precisely matches the theoretical expectation, providing another remarkable confirmation of general relativity. The detection of gravitational time dilation around Sagittarius A star required extraordinary precision in measuring stellar spectra. Astronomers had to account for the star's orbital velocity, its rotation, atmospheric effects on Earth, and instrumental calibrations to isolate the purely gravitational contribution to the observed redshift. The success of these measurements demonstrates how black holes serve as precision instruments for testing fundamental physics. Future observations of stars orbiting Sagittarius A star will provide even more stringent tests of general relativity. As observational precision improves, astronomers will be able to detect higher-order relativistic effects, such as frame dragging, the tendency of rotating black holes to twist space-time around them. These measurements will test aspects of Einstein's theory that have never been probed directly. The Event Horizon Telescope observations of black hole shadows represent another powerful test of general relativity in the strong field regime. The size, shape, and brightness distribution of the observed shadows depend critically on how light rays bend in the curved space-time around black holes. Any deviation from Einstein's predictions would show up as discrepancies between observed and theoretical shadow properties. The circular shape of the M87 star shadow, accurate to within a few percent, confirms that the object has the geometric properties expected for a Kerr black hole. Alternative theories of gravity often predict different shadow shapes or sizes, making these observations a powerful way to distinguish between competing theories. The precision of current measurements already rules out several modified gravity theories that were previously considered viable. Polarization measurements of the light around black holes provide additional tests of general relativity through their sensitivity to the magnetic field structure in curved spacetime. The polarization patterns observed by the Event Horizon Telescope match theoretical predictions for how electromagnetic fields behave in the strong gravitational environment near black holes. These observations probe the interaction between gravity and electromagnetism under extreme conditions. The detection of gravitational waves from black hole mergers has opened an entirely new window for testing general relativity. When two black holes spiral into each other, they produce gravitational wave signals that carry detailed information about the masses, spins, and orbital dynamics of the merging objects. The observed waveforms match Einstein's predictions with remarkable accuracy across a wide range of black hole masses and spin rates. The chirp pattern of gravitational waves from black hole mergers provides a particularly sensitive test of general relativity. As the black holes spiral closer together, the frequency and amplitude of the gravitational waves increase in a pattern that depends on the detailed structure of space-time around the merging objects. Any deviation from Einstein's theory would show up as differences between observed and predicted chirp patterns. Post-Newtonian tests of gravity using gravitational wave observations have confirmed general relativity to unprecedented precision. These tests compare the observed evolution of black hole orbits to theoretical predictions that include corrections beyond Newton's theory. The agreement extends to effects that are 5 orders of magnitude smaller than the leading order gravitational wave signal, demonstrating the exquisite sensitivity of these measurements. The ring-down phase of black hole mergers provides another unique laboratory for testing general relativity. After 2 black holes merge, the resulting object undergoes damped oscillations that depend only on its final mass and spin. These quasi-normal modes represent the characteristic frequencies at which perturbed black holes return to equilibrium, and their detection confirms predictions about the fundamental nature of black hole spacetime. Black holes also serve as laboratories for studying the behavior of matter under extreme conditions that cannot be achieved in terrestrial experiments. The accretion disks around black holes contain matter at temperatures of millions or billions of degrees, densities comparable to atomic nuclei, and magnetic field strengths trillions of times stronger than Earth's magnetic field. These conditions allow studies of plasma physics, nuclear physics, and particle acceleration in regimes far beyond laboratory capabilities. The study of relativistic jets from black holes provides insights into particle acceleration mechanisms that operate throughout the universe. These jets accelerate particles to energies exceeding those achieved in the most powerful human-built accelerators, yet they operate continuously for millions of years. Understanding how black holes accomplish this feat could inspire new approaches to particle physics and energy generation. Observations of matter spiraling into black holes test our understanding of fluid dynamics and magnetohydrodynamics under extreme conditions. The transition from stable orbital motion to inevitable infall occurs at the innermost stable circular orbit, where the physics changes dramatically within a distance smaller than the black hole's gravitational radius. This transition provides a natural laboratory for studying the breakdown of circular orbital motion in strong gravitational fields. The extreme magnetic fields around black holes create conditions where quantum electrodynamics effects become important. In these environments, the vacuum itself can become unstable, producing electron-positron pairs through the Schwinger mechanism. While this effect is far too weak to observe in laboratory experiments, it may play a role in the physics of black hole accretion and jet formation. Black holes also provide unique laboratories for testing quantum mechanics in curved spacetime. The prediction of Hawking radiation emerges from applying quantum field theory to the curved spacetime geometry around black holes. While Hawking radiation is too weak to detect directly for astrophysical black holes, its theoretical prediction has led to profound insights about the relationship between quantum mechanics, thermodynamics, and gravity. The information paradox associated with black hole evaporation represents one of the most challenging problems in theoretical physics. Black holes provide a natural setting where the fundamental principles of quantum mechanics and general relativity come into direct conflict. Resolving this paradox may require new physics that goes beyond our current understanding of either theory. Holographic duality, inspired by black hole thermodynamics, has emerged as a powerful tool for studying strongly coupled quantum systems. The idea that the information content of a volume can be encoded on its boundary has applications ranging from condensed matter physics to nuclear physics. Black holes serve as the original inspiration and testing ground for these holographic ideas. The study of black hole mergers provides laboratories for testing physics under the most extreme conditions possible. During the final milliseconds before merger, the gravitational fields become so strong that they approach the Planck scale, where quantum gravity effects may become important. While current observations are not sensitive to these effects, future gravitational wave detectors may probe this ultimate frontier of physics. Black holes also serve as cosmic particle accelerators that produce some of the highest energy particles in the universe. Ultra-high energy cosmic rays, particles with energies exceeding 10 to the 19th electron volts, may originate from the environments around supermassive black holes. Understanding how these extreme energies are achieved could provide insights into fundamental particle physics at energy scales far beyond terrestrial accelerators. The magnetic field reconnection processes around black holes operate under conditions of extreme energy density and curvature that cannot be replicated in laboratory experiments. These processes may be responsible for explosive phenomena like gamma ray bursts, the most energetic electromagnetic events in the universe. Studying magnetic reconnection in black hole environments provides insights into plasma physics under extreme conditions. Future observations will extend the laboratory capabilities that black holes provide for fundamental physics. Next-generation gravitational wave detectors will be sensitive to space-time fluctuations at even smaller scales, potentially detecting signatures of new physics beyond general relativity. Advanced electromagnetic observations will probe closer to black hole event horizons, testing the predictions of strong field gravity with increasing precision. The combination of gravitational wave and electromagnetic observations from the same events will provide unprecedented insights into black hole physics. These multi-messenger observations will test whether gravitational and electromagnetic phenomena propagate at the same speed, probe the equation of state of matter under extreme conditions, and potentially detect signatures of exotic physics near black hole horizons. Precision astrometry missions will track the orbits of stars around black holes with accuracy sufficient to detect frame-dragging effects and other subtle relativistic phenomena. These observations will test predictions of general relativity that have never been directly verified and may reveal deviations that point toward new physics. The development of quantum sensors and atomic interferometry may eventually enable direct detection of gravitational effects from black holes that are currently beyond our reach. These technologies could detect the tidal effects of passing black holes or measure the quantum properties of space-time fluctuations in ways that complement gravitational wave observations. Black holes continue to push the boundaries of our understanding of fundamental physics, serving as natural laboratories where extreme conditions reveal phenomena that challenge our theories and inspire new discoveries. As our observational capabilities continue to improve, these cosmic laboratories will undoubtedly continue to surprise us with new insights into the deep workings of the universe. The precision tests enabled by black hole observations have confirmed Einstein's general relativity under conditions far more extreme than he could have imagined when he first formulated the theory. Yet, they have also revealed puzzles and paradoxes that point toward new physics waiting to be discovered. In this sense, black holes serve not just as laboratories for testing known physics, but as guides toward the unknown frontiers that await future generations of scientists and explorers. Our journey through the physics of black holes and light has brought us to a profound realization that challenges our most basic assumptions about reality. Black holes don't trap light by reaching out and grabbing it with invisible forces. Instead, they accomplish something far more fundamental. They reshape the very geometry of space and time so completely that all possible paths for light lead inward. This geometric picture of gravity represents one of the most beautiful and counterintuitive insights in the history of human thought. The paradox that began our exploration, how something with no mass can be trapped by gravity, dissolves when we understand that gravity itself is not what we thought it was. Newton's conception of gravity as a force acting across empty space gave way to Einstein's revolutionary insight that gravity is the curvature of space-time itself. In this geometric picture, objects don't fall because something pulls them. They follow the straightest available paths through a curved landscape of reality. This transformation in our understanding represents more than just a change in scientific theory. It reveals that the most fundamental aspects of existence, space and time themselves, are dynamic and malleable, rather than fixed and absolute. The stage upon which cosmic drama unfolds is itself an active participant in that drama, shaped by every particle of matter and every quantum of energy in the universe. The Event Horizon Telescope images that opened our story provide dramatic visual confirmation of this geometric understanding. The bright ring of light surrounding the dark shadow of M87 star shows us the last photons that can escape from the black hole's vicinity. These photons have followed geodesics through curved space-time that brought them right to the edge of the region from which escape is impossible. The shadow itself represents something profound about the nature of space-time geometry. It's not an object in the conventional sense, but rather a geometric boundary where the curvature becomes so severe that all future directed paths curve back inward. The photons creating the boundary of this shadow are following the straightest possible paths through space-time, yet those paths lead them on spiraling trajectories around the black hole before either escaping or being captured forever. Understanding light's interaction with black holes illuminates the deeper unity underlying all of physics. The same geometric principles that govern the motion of planets around stars also determine the fate of photons near black holes. The same space-time curvature that creates gravitational time dilation also bends the paths of light rays and creates the spectacular gravitational lensing effects we observe throughout the universe. This unity extends to the quantum realm as well. Hawking radiation emerges when quantum field theory meets the curved geometry of black hole space-time. The prediction that black holes have temperatures and can evaporate reveals deep connections between gravity, thermodynamics, and information theory. These connections suggest that space-time itself might emerge from more fundamental quantum information processes. The holographic principle, inspired by black hole physics, proposes that the information content of any region of space can be encoded on its boundary. This remarkable idea suggests that our three-dimensional experience of reality might be a projection of information stored on a two-dimensional surface. Black holes serve as the original motivation for this principle, with their entropy proportional to the area of their event horizons rather than their volumes. The study of black holes has also revealed the fundamental role that information plays in physics. The information paradox, the question of what happens to information that falls into black holes, has driven decades of research into the foundations of quantum mechanics and general relativity. The proposed resolutions to this paradox suggest that information might be more fundamental than matter or energy, forming the basis from which space-time itself emerges. Our exploration has shown how black holes serve as natural laboratories for testing the most extreme physics in the universe. The gravitational fields around these objects are so intense that they reveal phenomena invisible under ordinary conditions. Time dilation becomes measurable, space-time curvature becomes observable, and the geometric nature of gravity becomes undeniable. The precision tests of general relativity enabled by black hole observations have confirmed Einstein's theory under conditions far more extreme than he could have imagined. Yet these same observations have revealed puzzles and paradoxes that point toward new physics waiting to be discovered. The marriage of quantum mechanics and gravity, still incomplete after decades of effort, may finally be consummated through insights gained from black hole physics. The technological achievements required to observe black holes directly represent triumphs of human ingenuity and international cooperation. Creating a telescope the size of Earth to image the shadow of M87 star required coordination between observatories on multiple continents, sophisticated data processing techniques, and years of careful analysis. The detection of gravitational waves from merging black holes demanded instruments sensitive enough to measure distance changes smaller than 1/10,000th the width of a proton. These observations have opened new windows into the universe that complement and extend our understanding beyond what electromagnetic astronomy alone could achieve. Gravitational wave astronomy allows us to study black holes in ways that bypass the complexity of electromagnetic interactions, providing direct access to the dynamics of space-time itself. The future promises even more remarkable discoveries as our observational capabilities continue to advance. Next-generation telescopes will image black hole shadows with unprecedented detail, potentially revealing the photon rings that encode information about multiple light orbits around the black hole. Space-based gravitational wave detectors will be sensitive to mergers of supermassive black holes, events that may be accompanied by spectacular electromagnetic displays. The combination of gravitational wave and electromagnetic observations will provide multi-messenger astronomy that reveals aspects of black hole physics invisible to either technique alone. These coordinated observations will test whether gravitational and electromagnetic effects propagate at the same speed, probe the behavior of matter under extreme conditions, and potentially detect signatures of new physics near black hole horizons. As we develop quantum technologies and improve our understanding of information theory, we may eventually be able to probe the quantum aspects of black hole physics directly. The subtle correlations predicted to exist in Hawking radiation might someday be detectable, providing a window into the quantum structure of space-time itself. The philosophical implications of our journey extend far beyond academic physics. The realization that space and time are dynamic and malleable challenges our basic intuitions about the nature of existence. If the geometry of reality can be warped and twisted by the distribution of matter and energy, then our everyday experience represents just one possible configuration of a much richer and more flexible universe. The geometric picture of gravity also provides a new perspective on causality and determinism. In Einstein's universe, the future is not predetermined by forces acting across space, but rather by the geometry of space-time itself. This geometric determinism is both more subtle and more fundamental than the mechanical determinism of classical physics. The study of black holes has revealed the deep interconnections between seemingly disparate areas of physics. Thermodynamics, quantum mechanics, general relativity, and information theory all come together in the study of these extreme objects. This convergence suggests that our current division of physics into separate fields may be artificial, with black holes serving as bridges between different domains of knowledge. The information theoretic aspects of black hole physics have implications that extend far beyond astrophysics. If space-time emerges from quantum information, then the fundamental nature of reality might be computational rather than geometric. This perspective could revolutionize our understanding of everything from cosmology to consciousness. The practical applications of black hole research, while not immediately obvious, have historically led to unexpected technological developments. The mathematical techniques developed for analyzing black hole physics have found applications in fields ranging from computer graphics to financial modeling. The precision measurement techniques required for gravitational wave detection have spin-off applications in materials science and quantum technology. Perhaps most importantly, the study of black holes reminds us of the power of human curiosity and imagination. These objects were predicted by mathematical theory decades before they were observed directly. The fact that we can now photograph the shadows of black holes and detect the gravitational waves from their mergers represents a remarkable validation of the human capacity to understand the universe through mathematical reasoning and careful observation. The journey from Einstein's original prediction of black holes to their direct observation spans over a century of scientific progress. This timeline illustrates how theoretical insights can take generations to be confirmed observationally, requiring the development of new technologies and experimental techniques. The patience and persistence required for such long-term scientific projects demonstrate the best aspects of human civilization. As we conclude our exploration, we return to the image that began our journey, a photon approaching the event horizon of a black hole. In our initial, intuitive picture, we might have imagined this photon struggling against some mysterious force, fighting to escape, but ultimately being overwhelmed and dragged inward. Now we understand the true story is far more subtle and beautiful. The photon follows the straightest possible path through the curved geometry of space-time, never experiencing any force, never struggling against anything. It simply travels forward along its geodesic, which happens to curve back on itself in the warped space-time near the black hole. From the photon's perspective, if we could imagine such a thing, it's traveling in a perfectly straight line through flat space-time. This photon's journey represents the ultimate expression of Einstein's insight that gravity is geometry. The curvature of space-time determines the photon's fate not through force or coercion, but through the fundamental structure of reality itself. The photon doesn't fall into the black hole. It follows the shape of existence as it curves back toward the center of the gravitational well. As the photon spirals inward, its path traces out a geodesic through space-time that carries information about the geometry it has traversed. Even though this particular photon will never escape to tell its story, its journey is part of the larger narrative of how black holes shape the structure of space-time throughout the universe. The final moments of the photon's journey take it past the event horizon, through the ergosphere if the black hole is rotating, and ultimately toward the central singularity where our current understanding of physics breaks down. Yet, even in these final moments, the photon continues to follow geodesics, obeying the geometric laws that govern all motion through curved space-time. This photon story illuminates the profound truth that black holes reveal about the nature of reality. They show us that the universe is not a collection of objects moving through empty space under the influence of forces, but rather a dynamic geometry where matter, energy, space, and time form an interconnected whole. In this geometric universe, the paths available to light, and indeed to all matter and energy, are determined by the shape of existence itself. The grip that black holes exert on light is not the grip of a hand grasping an object, but the grip of geometry defining the possible paths through reality. It is the grip of space-time itself, curved and twisted by the presence of extreme mass and energy, into configurations that make escape impossible. Understanding this geometric grip transforms our appreciation of black holes from cosmic monsters into windows into the deepest workings of the universe. As we stand at the threshold of even more remarkable discoveries about black holes and the nature of space-time, we carry with us the profound insight that reality is far stranger and more beautiful than our everyday experience suggests. The universe is not just a stage for cosmic drama, but an active participant whose very shape and structure determine the possible stories that can unfold within it. In learning how black holes trap light without touching it, we have discovered something fundamental about the nature of existence itself.